The ignition system, like all processor-controlled systems, consists of inputs, the processor, and outputs. This simplified circuit illustrates this relationship. The processor uses multiple inputs to control multiple outputs, making adjustments for many operating variables. This diagram shows the major components of the ignition system. The input devices are the engine position sensor and intake manifold absolute pressure sensor. The ECM is a processor and an input device to the ignition control module, or ICM, which is also a processor. The ICM outputs a signal to the coil-on plugs mounted on each of the spark plugs. Click on the System Inputs to continue. Click on the segment that you wish to learn about. The input signals for the ignition system are from the manifold absolute pressure sensor and the engine position sensor. Click on one of the sensors to continue. Click on the remaining sensor to continue. Click on the sensor that you want to learn more about. The manifold absolute pressure sensor is mounted in the intake manifold after the throttle assembly. The manifold absolute pressure sensor, or MAP sensor, is a transducer that generates an input signal to the ECM proportional to the air-fuel mixture pressure in the intake manifold. The ECM uses this signal to adjust the base timing and as an input for air mass calculation. Remember, the manifold pressure after the throttle plate may be different from the turbocharger boost pressure. The engine position sensor is mounted in the gear cover. The engine position sensor measures the position of the engine camshaft by the use of a variable reluctance sensor and 7 cast protrusions located on the rear of the camshaft gear. Whenever the cam gear protrusions pass the engine position sensor, the deflection in the sensor flux line generates an alternating current signal to the ECM. Six of the 7 cast protrusions on the cam gear are located 47 crankshaft angle degrees before top dead center, 1 protrusion for each of the 6 cylinders. The engine position sensor sends a signal to the ECM based on these protrusions passing the end of the sensor. The ECM determines proper ignition timing and engine speed based on these signals. The 7th protrusion on the cam gear is located 30 crankshaft angle degrees after cylinder number 4, the last cylinder in the firing order, or 90 crank angle degrees before the protrusion for cylinder number 1. Because of its location on the gear, the signal from the 7th protrusion breaks the consistent time interval of the signal from the other 6 protrusions. The ECM interprets this 7th signal input as the beginning of a new cycle in the firing order and generates a timing reference signal for the ICM. Both the engine control module, or ECM, and the ignition control module, or ICM, act as processors for the ignition system. Click on the ECM to continue. Click on the ICM to continue. Click on the component you want to learn about. The ECM is mounted on the left side of the block toward the rear of the engine, behind the ICM and the mounting plate. The ECM uses the frequency of the signal resulting from the 6 evenly spaced cast protrusions passing the engine position sensor to calculate engine speed, and with the map sensor input, adjust the ignition timing. The ECM recognizes the 7th signal from the 1 unevenly spaced protrusion as the indicator for the start of a new cycle. Each cycle begins with cylinder number 1 as the next cylinder to fire. The ECM uses this signal to generate the spark reference signal for the ICM. The spark reference signal is a signal from the ECM to the ICM. The spark reference signal indicates to the ICM that cylinder number 1 is next in the firing order and commands the ICM in and out of multiple spark discharge mode. The multiple spark mode of operation will be discussed later in this section. The ECM receives the input for this signal from the engine position sensor and the 7th protrusion on the camshaft gear. There is 1 spark reference signal for each 6 spark timing signals. The spark timing signal to the ICM defines the ignition timing for each cylinder. This timing signal is defined by the manifold absolute pressure sensor and the engine position sensor inputs. The ECM uses these signals to make timing adjustments and sends a spark timing signal to the ICM. Utilizing the ECM to control engine timing eliminates the need to check or adjust engine timing. In this segment, we will look at the Ignition Control Module, ICM. The ICM is located on the side of the engine near the rear of block in front of the ECM. The ICM has the engine firing order of 1, 5, 3, 6, 2, 4 built into its memory. After establishing cam synchronization during startup, the ECM sends the spark timing and spark reference signals to the ICM. After receiving spark reference signal from the ECM, the ICM fires the spark plug for cylinder number 1, then the next spark plug in the correct firing order each time it receives a spark timing signal. After firing all plugs, the ECM sends another spark reference signal to start the sequence over. Although engine timing is controlled by the ECM, not the ICM keeps track of the firing order and fires each plug in the correct sequence. The ICM is a multiple spark discharge, capacitive discharge, high-energy type ignition system. The ICM contains a DC to DC converter and a separate coil drive for each spark plug. The DC to DC converter steps up the 12-volt battery supply voltage to 300 volts. This voltage charges the capacitor in each of the coil drivers. Spark timing signal received from the ECM causes the ICM to close the trigger switch, sending current flow from the ICM capacitor to the coil-on plug. Multiple spark discharge technology uses solid-state devices to trigger the capacitor charge-discharge discharge cycle very rapidly when the engine has low intake manifold pressure. During this condition, there is a relatively small amount of air-fuel mixture in the cylinder, and the cylinder is relatively cool. It is possible for the flame created by the spark to quench, that is, extinguish, due to the low heat and sparse air-fuel mixture in the cylinder. Combustion requires fuel, oxygen, and heat to sustain itself. If the plug is cooler than the minimum temperature required for combustion to sustain itself, or if the plug absorbs heat from the burning air-fuel mixture until the heat drops below the threshold, the fire will quench. If the cylinder contains too few air-fuel molecules when the plug fires, combustion may not start, may start and die. Firing the plug multiple times greatly improves the chances of a successful cylinder firing under these circumstances. We have already mentioned in this discussion how the ECM sends 6 spark timing signals and a spark reference signal for each cycle of the firing order. The ECM commands the ICM to enter the multiple spark discharge mode by the length of the spark reference signal. The signal for multiple spark discharge is approximately 4 times the duration of a spark reference signal for single spark discharge. The ECM commands multi-spark discharge based upon manifold pressure. When manifold pressure is increasing, ECM commands the ICM to deliver multiple spark discharge until pressure at the MAP sensor is 7 psi or greater. As the manifold pressure increases, flame quenching is not an issue. There is more air-fuel mixture available to ignite, and higher cylinder pressures create higher cylinder temperatures. These conditions favor combustion. Also, higher cylinder pressures require higher voltages to arc the spark plug gap, which requires a high voltage or hotter spark. At higher manifold pressures, the ECM reverts to normal 1 spark per cycle firing. When manifold pressure is falling, the ECM commands the ICM to deliver multiple spark discharge when pressure drops to 5 psi or less, and the ICM again fires the plug 3 times. The hysteresis or difference in pressure to turn multiple spark discharge off and on, depending upon pressure increasing or decreasing, prevents switching in and out of multiple spark discharge repeatedly in the 5 to 7 psi manifold pressure operating range. The ECM commands multiple or single spark discharge by varying the length of the spark reference signal to the ICM. Multiple spark discharge at low speed or power conditions results in better spark plug life and less chance for engine misfire. This section discusses how the output signals of the ignition system are used to ignite the air-fuel mixture in the cylinder to cause combustion. In this section, we will look at the coil-on plug and the spark plug. Click on the coil-on plug to continue. Click on the spark plug to continue. Click on the component you want to learn more about. C8.3250GN uses a coil-on plug type of ignition coil. This coil mounts directly to the spark plug. The high voltage pulse from the secondary windings of the coil are delivered directly to the spark plug. This system eliminates traditional spark plug wires, resulting in less maintenance and a more efficient transfer of electrical energy from the coil to the plug. 300 volts from the ICM coil driver flows through the primary windings of the coil-on-plug resistive coil. As the magnetic field is created by current flow in the primary windings, it induces a voltage in the secondary windings of the coil. Voltage rises in the secondary windings till it overcomes the resistance caused by the gap between the spark plug center electrode and the spark plug ground strap. A note of caution is needed concerning a coil-on-plug device. These coils have an input voltage of 300 volts and are capable of delivering voltages as high as 40,000 volts. While the coil shock is usually not fatal, the secondary reaction may cause a serious accident. For this reason, it is important for you to take precautions when working around the ignition system to avoid shock. Whenever possible, shut off the engine before performing service. The ICM has a built-in engine protection feature. The ICM monitors the high voltage pulse to cylinders number 3 and number 4 to determine if these coils are firing. Anytime the continuity of the signal wire, return wire, or primary winding for cylinder number 3 or number 4 is broken, the high voltage pulse from the ICM is prevented, and the ICM ceases the discharge to all coils. Therefore, removing the harness at the number 3 or number 4 coil, or from the ICM, shuts down the engine. A spark plug is installed for each of the 6 cylinders in the spark plug bores in the cylinder head. The spark plug design and its condition are critical to engine performance. Because of the extreme conditions in which it operates, the spark plug used for the Cummins C8.3250G is not a standard automotive type plug. The plug utilizes a nickel alloy electrode. Additionally, the center electrode has a platinum insert and the ground strap has a platinum pad to improve conductivity and provide reliable operation. New plugs are pre-gapped. They may be visually inspected, should not be gapped or cleaned. As discussed earlier, when the piston reaches the correct spark advance position in the compression stroke, the ICM closes the switch to the ignition coil. The ignition coil then delivers this high voltage to the spark plug. The resulting voltage creates a potential difference between the center electrode and ground strap. The voltage continues to build until it is great enough to cause current flow across the air gap between the electrodes. The center electrode is negative with respect to the ground strap. Therefore, the current flows from the center electrode down to the ground strap in a negative to positive direction. The voltage applied to the spark plug has to overcome not only the resistance of the plug gap, but also the resistance created by the air-fuel molecule in the gap. When voltage is high enough to overcome this combined resistance, current flows through the air-fuel molecules. The current flow and atomic movement combine to create a heat path of approximately 30,000 degrees Fahrenheit, igniting the air-fuel mixture. The amount of voltage required to fire a spark plug depends on the plug gap, cylinder pressure, and air-fuel turbulence at the time of the coil discharge. Higher cylinder pressure or a wider plug gap places more air-fuel molecules between the electrode and ground strap, increasing the energy required to establish the current flow. Turbulence between the electrode and ground strap requires more energy to prevent the arc from being distorted. 15,000 to 25,000 volts may be required to fire the plug at rated speed and power the properly tuned ignition system. Higher voltages will be required for a cylinder with worn components. Plug continues to arc until the energy in the secondary winding is dissipated below the breakdown voltage or until the switch is opened, removing the capacitor from the circuit. This allows the capacitor to charge for the next cycle. The C8.3250G engine operates at close to diesel-like cylinder pressures, which require a very durable spark plug. The plug integrity must be capable of 25,000 volts dielectric strength for extended periods. The spark electrodes must provide extended life high breakdown voltages, and the plug must fit into the limited cylinder plug well space. The C8.3250G engine uses a spark plug with 14 mm threads and a 3/4 inch thread length. It looks much like a typical automotive spark plug, but it is very different from over-the-counter automotive spark plugs. The center nickel alloy electrode with its integral platinum insert delivers the electrical energy for the spark to the ground. The ground electrode or ground strap receives the electrical energy from the center electrode and conducts it to ground. The ground electrode has a platinum pad. The use of the integral platinum insert and the platinum pad provide excellent conductivity and reliability for dependable service. It is important to remember that the platinum is extremely soft and can be damaged easily. Proper handling of the plug is critical. You must never re-gap the gap of the spark plug or it may become damaged and unusable. This center electrode and ground strap both have a copper core to aid in heat transfer away from the tip of the plug. The air gap separates the two electrodes. The electrical arc across this gap creates the heat that starts the combustion process. The air gap, cylinder pressure, and air-fuel ratio and air-fuel swirl determine the voltage required to arc the gap. As the plug wears, the gap increases, requiring an increased voltage to arc across the gap. The lower and upper seal rings are made of copper and seal the cylinder gases from escaping between the ceramic body and the metal shell. The threads allow the spark plug to be torqued in the engine cylinder head. The relationship between the threads, shell, and upper and lower sealing rings is critical. If the plug is over-torqued in the head, the threads may strip on the shell or in the cylinder head. Also, over-torque may distort the shell and cause sealing ring failure. If the plug is under-torqued, gases may leak between the threads of the shell and the head. The heat from the exhaust gas can cause the plug to seize in the bore, making it impossible to remove the plug without damaging the cylinder head. Under-torquing also prevents good heat transfer from the plug to the surrounding metal. When the plug is only lightly torqued, the plug is in contact with less of the surrounding metal. This does not provide adequate surface area for the plug to transfer heat to the cylinder head. When the plug is properly torqued, the contact surface area increases, providing for better heat transfer. The coil-on plug has a grounded mounting pad for secondary wiring return. The mounting pad is on the right side when the opening for the wiring harness connector is facing you. Inside the coil housing, this grounded pad is connected to the ignition control module return line. This wire is the return for the coil driver. Most of the current flow through the secondary windings goes through the ground in the mounting pad. This isolates it from the ICM circuitry and improves the noise immunity of the ignition system.